name is Pavitra Tangavela. Today my team members and I are going to present about magnetic circuits. So for my part, I will cover the definition and types of magnetic circuits. So first of all, a magnetic circuit is made up of one or more closed loop part containing of magnetic flux. This magnetic flux produced due to flow of current that passing in a coil and generated by electromagnets. Besides that, the direction of magnetic flux is followed by right-hand thumb rule. This rule states that hold the conductor in right-hand thumb point and current passing through it, while curved fingers will give the direction of magnetic flux. In addition, the characteristic of magnetic flux is it never intersect and opposite poles attract to one another. Last but not least, there are three types of magnetic circuits. First is series magnetic circuits to find flux. Second is series magnetic circuits to find Ni, and lastly is series parallel circuits.
Hi, my name is Mitra Hidayah. I'm going to cover about series magnetic circuit. Okay, the series magnetic circuit that having number of parts of different dimension and materials carry a same magnetic field. This is the ferromagnetic iron material circuit. There are four basic steps to calculate the series magnetic circuit. For the first step, draw the equivalent ampere circuit law model. Second, compute flux density for each section by using flux over area. Third, determine magnetizing force for magnetic section from the flux density minus magnetizing force. This one we have to look for the table. 4. Compute magnetic flux equal to Ni by using ampere circuit law. This is the example for calculate the series magnetic circuit. From the question, we know they want us to find the value of current required to develop a magnetic flux. So from here we know that they already give the value of flux, area and length, number of coil turns, and we also know that the material of this magnet. So they want us to know the current value. So we will follow the four basic steps. This is the first step to calculate the series magnetic circuit. Draw the equivalent ampere circuit law model. So this is from the equation that they give us. So we have to draw like this. So we label also the area, flux, number of coil turns, length, and the material that they use. So from the magnetic circuit, we will draw also the electric circuit. So here is electric circuit. For the second step, we must compute flux density for each section by using flux density equal flux over area. So they already give the flux value and the area value. So we just key in the value into the formula. So we got the 2 times 10 power of negative 1 Tesla. Okay, for the third step, we have to determine magnetizing force for magnetic section from the flux density to magnetizing force curve. So here we have to know the material that we use, either cast iron or steel. So from the equation we know that we use the cast iron. So we just use the value of the cast iron here. This one 155,080 per minute. Okay, this is the last step. We have to compute Ni by using ampere circuit law. So we got already the formula HL equal to Ni. So from here we know that they already give the length value and number of coil turns. So we just key in the value into the formula. So 1550 ni this is cast iron value times with length value 0.16 m and divide by 400 number of turns. So we got the answer is 620 ampere.
Hi, my name is Ganeshan. I'm going to cover the part of paramagnetic circuit. Paramagnetic circuit having two or more than two paths for the magnetic flux. Its behavior can be compared to the paraelectric circuit. Moreover, the paramagnetic circuit contains two different dimensional areas and materials having various number of parts. This is the equation for the paramagnetic circuit. Iron core is used in this circuit. This figure shows the iron core can be represented by the magnetic circuit. The iron core has a cross-section of 2 cm by 2 cm and a relative permeability of 1000. The iron core has 500 turns and carries a current of I equal to 2 ampere. For this question, we need to find the flux density in each air gap. First, we compute the reluctance of three paths. This is the equation for finding RC, whereby the LC is represented the path of central. Mu R is represented the permeability of core material, and mu naught is represented the permeability of free space, and A is represented the cross-sectional area, and we get the value of RC is this. Then bear in mind that reluctance is in the unit of ampere turns per vapor. For the left-hand path, the total reluctance is the sum of the reluctance of iron core plus the reluctance of gate A. We take freezing into account by adding the gap length to its width and depth in computing area of the gap. Thus, the area of gap A is area equal to 0.9 mm². Then, the total of the reluctance of left-hand path is this equation. And then we substitute all the information into this equation, we will get the answer of this. Similarly, for the reluctance of the right-hand path is equal to this equation. And then we substitute the information for the right-hand path into this equation, we will obtain this result. Next, we can combine the reluctance of reluctance A, which is reluctance of left-hand path, and R reluctance B, which is reluctance of right-hand path in parallel. Then the total reluctance is the sum of RC, and this is the combination of the equation. Then we substitute the value into this equation, we will obtain this value for the reluctance total after combination. Now the flux in the central leg of the coil can be found by dividing the magnetomotive by force by the total reluctance, which is this equation, and then we will obtain this value for the total reluctance. Flux are analogous to current, thus we use the current division principle to determine the flux in the left hand and right hand path, resulting in this equation, and then we substitute the value, we get this value for the flux. These are the methods that we use to solve the paramagnetic circuit.
Hi everyone, I'm John Viet. Today I would like to talk about the series parallel magnetic circuit. This is an example for the series parallel magnetic circuit. As we know, a magnetic circuit can be looked as the electrical circuit. And the V1, which is the magnetic flux entering the node, is equal to the V2 and V3, which is the magnetic flux leaving the node. And in the electric circuit, the resistor symbol is represented as the reluctance in the magnetic circuit. And HL is the MMF drop as in the magnetic circuit here. We can also apply the KVL in the circuit to obtain a certain value of HL or H. Let us assume the magnetic circuit is made by a ferromagnetic material, which is the steel. And now, if we have the H value here, we can obtain the V value from the VH graph. It's like that. Vice versa, if we have the V value here, we can also obtain the H value here, only in the steel. But this H value cannot apply in the Hg here, because Hg is the H in the area is not made by the steel. Every different ferromagnetic materials have different reactive permeability μr, and this μr value will affect the curve in the VH graph. And now we will show you the calculation of the series parallel magnetic circuit. Here is the example for the series parallel magnetic circuit, and this magnetic circuit is made by the Castillo. And now this is the information given by the question. This magnetic circuit can be represented by a approximated electric circuit. For the A game, the magnetic flux density is equal to Vg over Ag, which is the value of 0.3 Tesla. And from this value, we can get the Hg value, which is equal to 2.388 times 10 to the power of 5 AT per M. The magnetic flux density of AGF, CD, and DA is equal to 0.3 Tesla. They all are the same. And from this value, we can get the HAV, HCD, which is equal to 250 AT per M. This value is get from the VH curve. Here is the example for the VH curve. And now we are using the Castillo, so we just look at the Castillo line. Now we apply the Ampere's law in the loop 2. Since the Ni is equal to 0, so we apply a KVL here. HAV, IAV plus the A gap here, HGIG plus HCD, ICD, and minus HDA, IDA is equal to 0. And now we have the HDA value. Same here, we have the HDA value. Now we can get the VDA value from the VH curve. And now we have the VDA value. We times the A and we get the V2 here. And now V1 is equal to V2 plus V3 and equals to 2.84 times 10 to the power of negative 2. And the V1 here over A is equal to 1.42 Tesla. This is for the magnetic flux density for VDEA. This VDEA value can help us get the HDEA value. This is also from the VH curve. And now we apply the Ampere's law in the loop 1 here. and I is the source for the magnetic circuit, and is equal to HDEA IDEA plus HAD IAD, which is equal to 929 AD. And now we can get the I value here, which is equal to 4.65 ampere. That's it. Thank you.
Hi, I'm Lily. For my part, I'm going to talk about the similarity and the difference between three types of magnetic circuit and their application. Okay, let us start to talk about the similarity and the difference between the three types of the magnetic circuit. For these three types of magnetic circuit, there are some similarity characteristics. First, the core for these three types of magnetic circuit are made by ferromagnetic material. These three types of magnetic circuit can be represented by an approximate electric circuit. In addition, these three types of magnetic circuit need to consider the reluctance made by an air gap. We can use KVL theory to solve these three types of magnetic circuit. Moreover, the magnetic field intensity H or magnetic flux density B value can be obtained in the BH curve based on the ferromagnetic material. Okay, let us talk about the difference between the three types of magnetic circuit. From this table, we can see that the series magnetic circuit, parallel magnetic circuit, and series parallel magnetic circuit has different characteristics. The series magnetic circuit, the flux is same for all sections, but for the parallel magnetic circuit and series parallel magnetic circuit, the flux is different at the different sections. Next, for the series magnetic circuit contains two cores, but the parallel magnetic circuit and the series parallel magnetic circuit contain three cores. In addition, the core in the series magnetic circuit and the series parallel magnetic circuit is widened at the left-hand side, while the parallel magnetic circuit, the core is widened at the center. The total reluctance for the series magnetic circuit is calculated as a Rp equal to R1 plus R2 plus Rg. And for the parallel magnetic circuit, the total reluctance is calculated as a Rt equal to 1 over R1 plus 1 over R2 plus R3, which the reluctance at the left-hand side is parallel to the reluctance at the right-hand side. While for the series parallel magnetic circuit, the total reluctance is calculated as a Rt equals to 1 over R1 plus 1 over R2 plus R3, which the reluctance at the center is parallel to the reluctance at the right-hand side. Lastly, series magnetic circuits can only apply KVL to solve the magnetic circuit, while for the parallel magnetic circuit and the series parallel magnetic circuit can be applied both KVL and KCL to solve the magnetic circuit. Okay, now I'm talking about the applications for the magnetic circuit. Magnetic circuit can found in a motor, generator, transformer, and so on. This is a figure for the motor, and this is for generator, and this is for transformer. Magnetic fields can be created by electric currents and permanent magnet. Magnetic strip contains information, so it mostly used in ATM card, library card, and so on. Magnetic circuit guide flux to an air gap. This provides fuel for the voice coil. Magnetic circuit also used in a speaker and microphone. This is the figures for the speaker and this is the figure for the microphone. Electromagnetic effects are the moving force in the design of the speaker and the microphone. In conclusion, I wish to sum up to the electromotive force and indirectly proportional to the reluctance in a circuit. From this assignment, we able to represent the magnetic field using Faraday flux concept. Moreover, we also learn to describe magnetic field quantitatively in the terms of flux and flux density. In addition, we also able to determine the magnetic field intensity using magnetic flux density from BH curve. Last but not least, we able to solve the series and parallel magnetic circuit. That's all for our assignment. Thank you.